Hello, everybody, and welcome to Thursday, April 8th. It's after spring break here. Mr. Parrott here with your rundown of stuff happening for the week after spring break. We just came back from a leadership academy, so we did our Great Fossil Find on Tuesday, so make sure you turn in the Great Fossil Find activity. You should have found all that stuff online. Check out Tuesday's video to check where all that stuff is at. You got your bell ringer up there for a day, so make sure that you answer up your bell ringer. We'll also have a March Mammal Madness update to do, as basically every day this week we'll be doing one of those updates because we're getting closer and closer to the finals, because really the finals already happened. We're just going through it since we missed the last couple of days of April there with our stuff. So what we're doing today is doing some little fossil notes. So let's dive into those notes. It is objective number 4 that we are doing. And the first thing that we got to do is we got to talk about the different types of fossils. Now, the first type of fossil that you commonly think of as a fossil is what is called a petrified fossil. And that is where the bones have been buried underneath rocks and other things and have had their bones actually mineralized into the fossil. So it no longer is the stuff that bones are made out of, but rather their bones have been replaced by minerals and other harder material to kind of solidify that stuff now that the living tissue is gone. That's what we commonly think of as a petrified fossil. The preserved fossils, on the other hand, those are things like things trapped in amber, things in the tar pits, things frozen in ice, where it is something that has been preserved in another substance other than buried underneath rocks. So if you think back to the Jurassic Park thing, the mosquito inside of the amber, that is the stuff that would be a preserved remain, because it still has other parts besides the bones that are still left there. So here's some more examples of some fossilized materials: shells, bones, even the impressions that are left back, but there are some bones in there. All that stuff can be considered to be fossils in one way, shape, or form. Then here's a preserved one of the baby mammoth in the corner there that they found trapped in ice, kind of mummified in there. Kind of see it's got a little bit of a tuft of hair right there. There's a little tuft of hair showing it. The other two types of fossils are what is called a mold and then a cast, which a mold is actually the thing that we would consider to be more of a fossil. It is the impression that gets left behind. So a hollow space, think of like a dinosaur footprint that gets left in the mud. That footprint stays in there so that later on we can see the footprint buried underneath rock because it's still contained there. That would be a mold. The cast then is what we do to we basically get this material together. That's kind of like what they do for a cast. It's the goopy stuff. And we basically lay that into the mold, and then we can get a 3D shape of whatever that organism was. So, for example, if we have our mold over here of this shell, you can pour this material into that, let it harden, remove that, and now you have a 3D representation of what that shell could have looked like from a 3D point of view, instead of just looking at the kind of hole that it left behind. So it's just a way to get a different perspective on the same thing going on there. So there's a picture showing the mold versus the cast then in the end. The mold would be that seashell, but you can't really see all the unique parts of that seashell from it being a hole in the ground. So you filled up with the plastery material that's there to create the cast, and you can see the more 3D represented shell in its full glory going on there. Which is how we learned about some of the different types of animals and whatnot, is from the molds that they leave behind, because they don't always leave behind bones, especially if they don't have bones, because some organisms don't have necessarily their internal skeletons, like bugs and stuff like that. And how we know about fossilized plants is also through molds and casts. So second thing that goes along with just what fossils are is how we can use them to date, and putting a time frame to these traits and what they had and when they might have changed to a new trait. We can do that in one of two methods. One is called relative dating, the other one's called radioactive dating. Relative dating is very simple. You have to have two fossils, and basically wherever you found them, how deep you go, the same layer of the earth that you find them in, it means that they're about the same age. So if you dig 20 feet down and find a fossil, and you go 20 feet down in another location and find a fossil, they probably are from the same time frame. If you go, let's say now, 100 feet down and find something, but you find something else at, let's say, like 50 feet, they could be from a different time frame. So depending on how far down you dig, could come out to be different ages. Typically what we say is that the closer they are up at top, they are younger. The deeper we have to go in the crust to find them, the older that they get. So this is just showing, younger and deeper. We just kind of rank them. It's not giving like a clear estimate of time. We just know which one's going to be younger and which one's going to be older. Now, problems with this is that this method is only really usable if the rock layers have been preserved. If there hasn't been any kind of major catastrophe that has basically shifted the ground enough to where things get jumbled up. Like if there's an earthquake or something, that usually messes things up because it moves the layers of the earth around. Or if there's like a mudslide or a rock slide, that kind of messes things up. And it can only be used to, that'll throw a wrench into a problem there. The second thing of why this can be a problem is that it can only use to compare two fossils. It can't actually tell the age of one fossil. So it's only good if you're saying like, oh, this one is younger than the other one because I found this one closer to the surface. It can't actually say like, oh, because I found this 20 feet down, this is from 50 years ago. It won't do something like that because it doesn't have the capabilities. You're just digging a hole and finding a fossil. So here's how something can be different based off of different things happening. So on one side, you have one part of the canyon. On the other side, you have another part. On the right side, which is over here, there is nothing happened to it. It was just fully intact. On the left side, there's a bunch of things that ended up happening to it. Let's say there was like a river came along or a flood happened and it washed out the bottom two layers of this canyon. So the fossils that were there are no longer there. There was a rock slide that happened and it caused all of layer 5 to be removed out of play. Also because the left side is slightly a different environment, they also had different animals over there that existed. So there's development of layer 7 and 8 because they have just a more unique environment. So they had more animals around in that area compared to the other side. So it doesn't really work out that nicely when things move around. And since nature is always unpredictable, a lot of things dealing with relative dating is, as it says in the name, relative. Are you in the same area? How far did you dig down? Is that comparable to the other section? We'd have to figure all that stuff out. The other version of dating is called radioactive dating, and what that actually tells us is the age of the fossil, and we do that through using radioactive material. So how it uses is that it basically uses the amount of radioactive element that is in the fossil and compare it to how much should be there. Because right now, in our own bones, we have radioactive elements going on inside of us, not giving us superpowers because that's not always how radioactivity works. It's just a different version of the atom is how radioactivity works. And inside our bones, we have a certain amount of radioactivity just going on naturally about us. Same with any living bone. So what we can do, we can take a look at how big the bone is. We can look at how much should be in there and compare it to how much is left. And from that, we can judge how long it's been sitting around for. Because the fun thing about our elements and about atoms is that they decompose at the same rate no matter where they are at. As soon as your bone starts living or stops or is dead and your life is done, the radioactive parts of your living cells will start to go away slowly. And it takes lots and lots of years for it to completely get removed to where you'll still even have some radioactive elements 60 million years later. Basically how that works is that they create this big old chart and they can predict the half-life of the atom throughout history because it takes a lot to lose your radioactivity. That's why radioactivity is kind of a dangerous thing, because it can last for a really long time for it. And basically they compare how much is there with how much is not there, and from that they can do some math and calculate out, oh, it's about 50 to 60 million years old, give or take, in somewhere around that range. Or maybe it's 20 million years old, because it's still got a lot more in there. So using their math that they do, they can help predict how much or how less there is. And because of that, we can create the basically history of events that is our geologic time scale, which goes all the way back from how they traced it, from the earliest known radioactive rocks that are around, 4.6 billion years old. That's as far back as how we can date. Now, whether or not that is the actual Earth's history or not, we don't know unless we build a time machine and go back there. But that is the estimation as of now using our fossil record, which is basically what we created off of this stuff in the Geologic Time Scale, the GTS. And from that, we can categorize when animals started to show up in our fossil record. And we can kind of make assumptions as to what things could have happened over the course of however many million years that things are around. To where we have, like, where dinosaurs are found, and where our mammals first come up, and where fish are found, and where, we got plants found in this area, not. So there's a bunch of stuff. And obviously, we can't find fossils because fossils are rare. In some cases, they get broken down over the years. They get lost. So this is only from things that we have found that are legitimate fossils in that case. To where we don't see too many things dealing with, mammals until closer up to the surface. Deeper you dig, the more reptiles and dinosaurs and kind of stuff you find, the deeper down that you dig. Our final thing dealing with fossils is extinction, because almost all species that are fossilized are extinct, meaning that no of them still exist. What we know about extinct species is solely from the fossil record and scientists putting 2 and 2 together, meaning all the stuff we know about dinosaurs is from extinction. Now, we do have these things categorized in our fossil records as mass extinction events. They occur when all of a sudden we don't see fossils appearing up for a long period of time. There's these gaps, and all of a sudden you don't see dinosaur fossils anymore, or you don't see these certain types of animals anymore. There's gaps, and this is what we consider a mass extinction event. And possible causes of those mass extinctions are things like climate change or environment changing. It's going to be drastic. There's the whole idea of asteroids hitting the Earth. There's that would definitely be an environmental change too. Or volcanoes erupting all at the same time. Or you have the ice age happening. There's a bunch of different theories out there of what causes these extinction events. Now, until we go back in time to those events and see them happening, we can only go off of our best logic at the time for how those things exist. And that is the end of objective number 4 in our notes for fossils today. There is no homework, so this would be the time where you can watch the March Mail Madness Update Tournament. We should be nearing the end of our bracket. Either our Elite 8 or our Final 4 should be happening at about this point. But we'll check out who is our victor soon enough here. So hope you're doing well, staying safe. Hope to see you back here soon. Until then, stay safe out there, and I will see you later. Bye.